Hello and welcome to Calculus 1. So this is our introductory lecture. We're going to define calculus and see what it consists of, and I guess what to expect to gain from knowledge of calculus. So first off, calculus is mainly study of change, right? And it developed over the years. It's about, some of the concepts are about 400 years old. So technically you are 400 years behind right now. But that's okay, you'll catch up quickly. So it's a study of change. It's been developed in 1600s. Two mathematicians came up with the concepts of calculus independently from each other. One of them was who? I see how it is. Isaac Newton, publishing his paper in 1666, right, on differential calculus. And then we have also Leibniz, who did the same thing. Newton focused more on physics and motion and gravity and use of the calculus for that type of a deal, where Leibniz focused more on finance and those kind of applications. And both dealt with geometry, obviously. So now we have something that it's been, around for about 400 years, and it hasn't changed since, right? Because once you have mathematical theorems and definitions, that's it. So you learn that, and you go from there. But it evolved to become much more accessible and easier to learn it than its original form. When you approach it from the geometrical perspective, it tends to be trickier. Also, the notation in the good old days was trickier, calculations were trickier, and especially that some of the tools that we have today, and I'm not talking about computers, some of the mathematical tools that we have today were not available at that time. So it was very interesting to see. So we know that calculus consists of three main parts. So we have limits. For us, that's going to be chapter 2. And then derivatives, which is chapter 3 and 4. And then integrals, which is chapter 5, but then also chapter 6 and 7 in Calc 2. So calculus consists of these three. And both Leibniz and Newton were in this number 2 with derivatives, right? Differential calculus. And they touched up on integration, but the concrete definition of limits and work on the limits actually came in 1800s. And then also integration was fully developed and worked out in 1800s. So we will see that limits provide the base for both derivatives and integrals. So we'll see those worked out as we move along. So technically, we are going to have firm knowledge of calculus already, and then in the Calculus 2, you will have the 2 extra sections on chapter 6 and 7 on integration, and then 2 sections on sequences and series, power series. And then finally, Calculus 3 is going to take all of this and redo and redefine everything in 3-dimensional space. So Calculus 3 is technically Calculus 1, but done in the 3D space. So mechanical engineering, electrical engineering, you guys are going to have lots of fun. Now, why study calculus? Well, if you take a look at the top sentence, right, calculus is the study of change. See, in pre-calculus and in algebra, concepts and ideas do not evolve, do not change. They're stationary, right? If you take a look at algebraic problem, it says simplify, right? And you have, so simplify in algebra, and it says, let's go, 3x to the 4th times 4x to the 5. Right? There is no change here. This is it, right? And you would say, okay, 3 times 4 is 12, and then 4 plus 5 is 9, so 12x to the 9. And you're done, right? Now you can say you go into the next course, which is pre-calculus, and in the pre-calculus you say compute f of 2 for f of x equals 12x to the 9. So this is your pre-calculus 1, right, concept. And you say, oh, okay, so that's the x. So if I plug in 2 over there, I better plug 2 over there, which is what the concept of the function means, right? So in that case, you know that you are supposed to say that f of 2 is equal to 12 times 2 to the 9, and that works out to be some kind of a number. Now we can easily compute that number because it is 2 to the 9th, and then you have another 2's, 2 2's from here because it's 4 times 3, so this is technically 3 times 2 to the 11 if you want some of the fast computing. So 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 22, so times 2048, and then this is 3 times that. So what do we have? We have 6,000, 1, 3, and no, 1, 4, and 4. 6144, I hope. You can start calibrating your calculators. So now that you have this idea, you start from algebra where you just have a concept, right? This is a rule that says if you're multiplying these x's that have the same base, right, you add the exponents. Then you go and you say, okay, but that could be a function. Now you have the input-output kind of deal. So if your input is 2, the output is 6,144. Did anyone, by the way, you just trust me? Oh, aren't you nice? Anyway, so now what's happening in calculus? Well, in calculus, we are going to focus on this function f of x, let's say 12x to the 9. And I would like to see the way this function changes if I apply, let's say, a limit to it, which is the concept that we are going to study today. So I can go and say limit of 12x to the 9 as x goes to 2. You see, now this is a calculus concept. This is going to give us the same number of 6144, but the concept is going to be a completely different than what we had in pre-calculus. We can also take the derivative, which will be denoted like this, of 12x to the 9, and get 90 and 18, so 108 x to the 8. Or we can do the integral. And all of these have their representations of what they mean. So you can see this 12x to the 9 go through all 3 concepts that we are going to learn. And the focus of the class should be on the meaning of these things and what we achieve by doing this. Now, in this classroom, the range of majors from what we heard, biology, computer science, to marketing, management, and we also have the mechanical engineer, right? Welcome. Calc 3 for you. Public policy, right? All the way from California, welcome. So, yeah, that's, so why is calculus so important to such a variety? Well, because, as I said, systems and things change. You are going to be the tallest and the lightest in terms of weight for the day when you wake up in the morning. As you go through the day, right, and you are walking, your joints compress slightly, so you are a fraction of an inch shorter by the end of the day. And then when you become horizontal, it will stretch out again. And also with the food, as you consume the food, because while you were unconscious for a number of hours, your body is still using a lot of resources and energy to just run the core, right? To run the heart and lungs and you know, move things around. So your body uses a lot of energy even in a passed out state. So when you wake up in the morning, you should be hungry. And if you are not eating, then you are not getting ready for not setting up for a good day. So systems change, and we want to understand those systems. We also want to make sure that we understand that as we are driving, right, the unfortunately still gas, right, is converted into energy, right, by exploding it in the engine block, and that pushes pistons, and pistons turn everything around, and about 25% or 27% at best of the energy that is generated in that way through combustion is used to move the car from point A to point B, and the other 75% is wasted on heat. So technically, every time you fill up your gas tank, you actually waste 3/4 of the money goes down the drain, goes to nothing, goes to heat, goes to noise, goes to all of these things, and only 1/4 of the money that you paid is actually the money that gets you from point A to point B. Compare that to electric vehicle. Does anyone know the efficiency on those, like Tesla? 95 to 97%. And the electricity is cheaper. So, at least from that point, right, where you have the absolutely terrible efficiency to something that's very efficient. So, there's that part. So we understand that. But then as you drive gas-powered car, the gas is used up, so the weight of the car is constantly going down, right? So there's the change in weight, and that happens over time. So we can measure that and detect that using calculus. And we can come up with a function that will tell you exactly what is the weight of the car at any given point. Moving on to, let's say, business and economics and so on, you might want to minimize or maximize something. For instance, you want to minimize the cost and you want to maximize the profit. You do that using calculus. We are going to see a few different examples that are related to these types of calculations, which are very, very important, obviously, in order to stay competitive and to run a successful business. So calculus is based and it's used everywhere and for anything. The question is how well you apply it in your area, and if you are able to realize and recognize the application of calculus in your area. And that's something that makes you really indispensable later on. If you are able to sit at a meeting, hear all these words, which hints the word problem, right? And then able to translate that into mathematical equation, which we call function, right, in this case, which you can apply one of the calculus concepts to understand things. For instance, we can take a look at population models. You dealt with population models in your pre-calculus course. Now, differential equations, which are studied briefly in Calculus 2, and then there are courses upon courses on differential equations afterwards, they teach you on how to obtain various population models. And obviously some of those are better than others. The most basic population model you guys learned in pre-calculus 1, and that was that the population in time depends on initial population times e to the some kind of rate of change of population k times t in time. So if you're talking about bacteria, that t could be in minutes or hours. If you're talking about, you know, animals and people, it should be in years. So you decide what, right? But again, the population model, this particular population model is extremely bad because the limit concept in calculus will teach us that if you are willing to wait for a very long time, the population goes to infinity. And we know that's bad because we cannot support infinite population of anything. It's impossible, right? There is carrying capacity of the planet that we have to worry about. So when you are looking at this and then you draw the basic exponential graph, right, which goes like that, understanding that this is your P0 initial population on the population axis and then time on the x-axis. As the time goes to infinity, your population goes to infinity, and we'll learn that from the limit concept. But then you can learn about the change in population, or how fast you're adding more people or bacteria or whatever you're adding by taking the derivative. Or you can learn on how many people or bacteria you had in the past from point A to point B by using the integral. So a lot of useful information. Now this would be something for biology and social sciences to worry about, right? Because we have to worry about these types of issues as we move on through the various problems that we have. So now when you are using the limit, you can see that this particular model for population is bad. And then you look for a better one. And the better one would be a logistics model. And a logistics model would have a graph that will start at P0 and then go up and level off. And now when it levels off, well, it levels off exactly where you have the carrying capacity. And the carrying capacity is going to be the maximum amount of people that you can have on the planet, right, that the resources can support. Or you're is going to be the maximum amount of people that can be infected by a certain disease, right? And so on. So, you know, the logistics models are much better. So in this case, when you send t to infinity, your population in time will be some critical population, or the, you know, carrying capacity population that we get. So calculus helps us understand these concepts. Calculus helps us learn about the change and how the systems and things evolve in time. Clearly, you know, the overused example that I generally don't use so much is, you know, the position and the speed and the acceleration, which are the concepts. I mean, we will go over it, obviously, in the class. It's extremely important, and, you know, Newton based his papers off of it. But as I said, you know, not everyone is interested in speed and position, and a lot of you might want to know about population and other concepts in life. Now, clearly, physics courses will cover everything in more in depth, but everything starts here. It's calculus concepts. Now, talking about the application, so this is you know, where the derivative tells us that the top model, which is the basic model, is bad and useless on the long run. Locally it works. The bottom one is much better because it levels off eventually, and we have a good representation. It's a really terrible graph, so I'm just going to redo the graph over here and, you know, put more OCD into it. We'll call that PK, that's P, that's P0, and that's time again. Yeah, much better. All right. So now that we are understanding that the limits are going to give us one thing, then for the same thing for population, I can take the derivative in time of population, and this will give me the change in population, i.e. number of new people, let's say, per year. I can say year. There we go. Now, if you carefully observe the notation, and if you regard this as a fraction and this is multiplied into that fraction, you can kind of see dp over dt, right? Which, if you look at the units, well, yeah, the population, the number of new people, that's the top, per year. Well, per year. Per year, right? It gives us the denominator is in time. So this gives us another thing to consider, right? So the derivatives will give us the change. Now, in some cultures, the population is going down because more people died and they have babies. In other countries, right, the balance is offset because of the wars or diseases. And then in some countries, you have the population go up because there are more babies and more advanced medicine. Then, I mean, we have to agree that the medicine is still at the like witchcraft level. It's just level 2, right? Instead of potion, we have a medication, but it's the same thing, right? We are not replacing organs and creating things as efficiently as we are doing with computers, and the reason is that the medical field is not mathematically mapped yet. A lot of institutions are working on it. Like MGIT is one of the leaders for neuroscience and brain mapping and so on, and a lot of biology in that department. But we are still not at the basic level where, okay, my kidney is not working, you print a new kidney and just plug it in. That's so we need to be at that point to actually go with the medical, 2.0. So when you are looking at all of these things, right, calculus ties again in all of it. And then the last concept over here would be the integral of population that we had in time, from time 1 to time 2, so from, let's say, 1999 to 2003. We can calculate the total amount of people that were around during those years. So integral will give me the sum of all people in interval t1 to t2, right, inclusive. So that's what the integrals do. They give us accumulation. They give us sum. So these three concepts together create calculus. And then in calculus 3, we take these three concepts and we put them in the 3D environment. We call it multivariable calculus. We can have more dimensions than 3, right? But we do 3D and 4D in Calc 3. So that's the basic roadmap for calculus. And in order to be successful in all of these things, as I mentioned earlier when we went over the syllabus, reading the book and understanding the theorems and definitions is the key. When you see a fork, right, you know the definition. It's a fork, right, used to scoop the food up, right, used for feeding and so on, right? So you know a definition of the fork. Some of you are going to define it different than others, but we all know what the fork is, and that's a definition. Now, the way you use it is called, in mathematics, it's called a theorem. You scoop the food, and you open your mouth, and you shove it in, right? That's very simple. that's mathematical theorem, right? And if the mathematical theorem is not followed, right, the right way, well, you end up stabbing yourself in the eye, and that's not fun. So learn math, right? So the same deal is going to be throughout this course. We are going to have a definition which will say limit is so-and-so, or derivative is so-and-so. And then once you have mathematical definition and you know what the terms on definition are, and what you're defining, then you have a mathematical theorem which says this is the way you calculate and compute things. And it will be very clear with our first theorem in our first lecture, 2.2, which is right after these intro words. We'll see a very important mathematical theorem that will stick with you throughout Calc 1, 2, and 3. And differential equations too. So it's going to be a very important theorem for limits. Now, what do we need in order to survive calculus? Well, we need the concept of a function. Calculus is done on functions. You take the limit of a function, you take the derivative of a function, and you integrate the function. But we also know that there are certain relations that are not functions, like circle, for instance. Circle is not a function. So we cannot integrate the circle. We have to, be creative in order to do certain things with relations that are not functions. So how about we define a function first? When we define a function, we are going to be able to... So here's our first definition of the day. And generally what I disclose this every time. If you choose to have an exam, this definition will be on your first exam, verbatim for 4 points. So you either know it or you don't. And I might put this one on another exam or a final, I don't know. But 100% on the first exam for 4 points, no partial credit, because you really can't state this in many other ways. The book states it a little bit different. You can use that one as well. But, the one that I'm going to show over here is the one that works. So function is a rule which assigns to each x in the domain a unique y in the range. So function is a rule which assigns to each x in the domain a unique y in the range. We are going to underline words rule, domain, range, and word unique is going to be underlined twice. So these are the four important words. Now notice that the word unique is underlined twice. It's a tricky word. If you remove this word, definition becomes relevant, but is for a different concept. It becomes a definition of a relation. And this is definition of a function. Okay, so this is definition of a function. So function is a rule. What do I mean rule? Rule as a formula, equation. We had it earlier, 12x to the 9, right? Y equals 12x to the 9. It's a formula that relates x and a y. So that is a rule. Domain, set of all possible input numbers. Now let's say values. Values. Range, set of all output values. And then word unique. Well, word unique, I'm just going to say that, I'm just going to rephrase the whole thing here. I'm going to say that word unique technically says that single x cannot produce multiple y's. Single input, which is x, cannot produce multiple outcomes, which is y. All right, so what is the graphical representation over here? You have x go into the function and y comes out. The notation for that is y equals f of x. And we have seen it before. You plug in value for x and you are able to compute y. Now those two create an ordered pair. An ordered pair is a point that you can graph, and then you can connect those dots into what we call a graph, and you have a graphical representation of your function. So these guys ultimately give you x, y ordered pairs. And those ordered pairs can go on the graph So it's important to understand that, you know, in cases of some of these functions, you have infinite amount of input points, which will create infinite amount of output points. But the ordered pairs are well defined because you have one x producing one y, and that's something. Now you can have multiple y, same y assigned to a few different x's. That's okay. Well, you can't have it the other way, where one x makes multiple y's. So now, when you connect all of those dots, you get what we call graph. Please make sure that you are calling this the coordinate system. That's not a graph, it's just a coordinate system. And the line you put on it is called the graph. So this over here is just a coordinate system. That's what it is. So we have the coordinate system, and in this coordinate system we have x and a y, and that's location. So if it's going to help, just look at the ceiling. You see the ceiling? It's coordinate place, coordinate system. You have these 2x2 tiles, and we can map location of every single person in this classroom. Just if you look up and you find the intersection, right? That's where you are. And we can set 0, 0 at any corner. Well, this room is octagonal, so it's going to have some very interesting mathematics over here. Good thing I'm not teaching Calc 3 in this room, because I need corners. I can't do it in this. But anyway, but you can find the location, right? We can set the location somewhere, and then you can go positive and negative x, positive and negative y, and figure out your location. That's what actually essentially GPS does. You know, when you from the satellite, right? You look at the Earth, becomes flat surface, right? You didn't know that? Anyone? Everyone's okay? All right, good. So it becomes this XY plane, right? And then you can go in the directions, forward and backward. Good. So now we have that concept. We have a test called vertical line test, which tells us whether the function, right, whether the relation is a function or not. If the vertical line cuts through once, it's a function everywhere. If it cuts 2 or more times, at least one spot, it's not a function. So circle is not a function, right, because the vertical line test will cut twice through the circle. Ellipse as well. hyperbola. So none of these things. And you know what they all have in common in their equations? They have y squared. So y to the even power is guaranteed not a function, right? Y to the even power. If you have y to the even power in your function, yeah, I mean, in your equation, it's not going to be a function. So that's that. Now, when I teach pre-Calc 1, which happened last year, I make sure that my students know that three concepts will never go away. And those are sections 1.6, 1.7, 1.8. 1.6 deals with transformations of functions, meaning shift left, right, up, down, stretch, shrink, horizontally, vertically reflect, and so on, with negative signs. So that section is important. It's extremely important to you guys because you don't have access to the graphing calculator, and a lot of functions are showing up on exams, right, and in calculus in general. So you need to be able to graph. And I'm going to write all of the rules pretty soon. The next section is the section on combinations and composition of functions. The most important derivative rule, called the chain rule, will be, and the most frequently used rule, is going to be the rule that it's done on function composition. For instance, sine x squared. You have a function x squared that is plugged into the function sine x. So it's called function composition. We will review that in detail, because without that, you're just not making through, not even by a long shot. You have to know it very well. And it's a backwards procedure for integration called U substitution. All the last lesson, 5.5, is going to be backwards chain rule, which is, again, a lot of this function composition kind of deal. And the third concept from that pre-calculus course that applies to all functions is inverse functions. So those are the three big concepts. Now, these concepts are not just, yeah, I'm surviving Calc 1. No, these are overarching concepts on functions. And they involve Calc 3 functions and so on. So we are going to have these concepts as, you know, concepts on functions that are extremely important. And then you have the concept of exponential functions and logarithmic functions from pre-calculus, which will be heavily used in calculus. And then clearly your trig functions from pre-calc 2 that will be extensively used. Now, we're not going to have too many of those identities in maybe, I don't know, 4 or 5 of them. But Calc 2, yeah, Calc 2 has a very heavy trig prerequisite requirement. So you'll need to brush up on that and be ready if you're going to Calc 2. So let's take a look at some of these basic ideas for shifting and so on. When you have a function, let's say we come up with f of x is equal to square root of x. All right? For square root of x, we would draw first the basic state for that function. It starts at the origin, and it goes like this. So this is the thing that you have to memorize, right? You are memorizing that the function has its default graph there. Now, if you don't know it, you'll have to compute the points and connect them, like right in a coloring book. Except you don't have to color, right? So you compute, 4 or 5 points, and then you connect the dots. Simple. So now you are almost never going to see root x. What you are going to see most of the time is going to be, let's say, f of x is equal to square root of x plus 2. Now see, this plus 2, when it's away from the, right, kind of added to the original function, is the shift up or down. So we can have, in this case, we can have f of x plus minus c. So plus c is going to be up, minus c is going to be down. That's obviously if c is larger than 0. So in our case, our square root function now is going to start at 2. It's going to look the same as the previous function. It's just going to start at 2. So you are picking this like the point at 0, 0, and you're just lifting that point 2 units up because the transformation said so. Your job is to lift the entire function up. Now, you have to understand, you have infinitely many points on this line. Each point from this line, and there are infinitely many, each point got plus 2 on y to go up and create this graph. So each point did that. Minus obviously brings it down, whatever amount of units you have. So if it's minus 1, it will start here and do the same thing. The next type of transformation would be to shift left or right. So now if I have f of x equals to square root of x plus 2 inside the square root. So now the modification is not on the entire function, modification is on the on x itself. Now these types of shifts are going to be left and right. So what I have over here is f of x plus minus c. You see the notation is different for these two guys. Notation is different because the top one is adding a number to the entire function. The one on the bottom adds a number to x directly. Now, when you have a plus c, the shift is left. When you have minus c, the shift is right. So now we have a plus 2, which means we go to negative 2 on x-axis, and we draw the same square root function. Now the next two transformations are not as important. They are shrinking or stretching functions. We have, let's say, f of x is 2 root x, or f of x is equal to square root of 2x. So this one is the horizontal stretch or shrink, and this one is vertical. The best functions to understand this would be the trig functions, obviously, but let me try with the square root of. So if this is the original one, square root of x, if you have 2 times that, that means that it's going to double. So this is 2 root x. Vertical stretch, it's much harder to see on the square root function. So when you stretch something vertically, right? Just think about stretching it, right? Sorry. Oh wait, I have these switched. Horizontal and vertical need to be switched, guys. I have them backwards. I said no tap dancing, right? So vertical, right, it stretches it up or down. And the best way to understand the vertical is waves. I don't know if you ever observed waves. I know you have, but and the people, they're my Florida people. You know, the best way to understand is vertical and horizontal stretches and shrinks is through trig function. If you have a sine wave, right, you can make that wave twice as large by multiplying it by 2, or you can make that wave faster, right, or you can make that wave slower, right? So there are ways of, and that's all done within these stretches and shrinks and so on. So you can understand that. And the last one is the reflection. So we can have f of x equals to negative square root of x, and f of x equals to square root of negative x. So the top one will push the function down, and the one on the bottom will reflect on y-axis, so it will push everything this way. Now, whenever you think like, okay, which one is which? Well, just think about, you are not allowed to take the square root of a negative number, right? Because it gives you imaginary. So look at this. It should be clear that I need to pick negative domain numbers. If I pick negative 1, and then I have this negative, negative and negative will give me positive, and the answer is 1. Yay! Right? It works. Over here, if I pick a negative number, well, it stays negative under the root, and there shouldn't be anything here, and it's not, right? So that's something that you have to be a little bit careful about. So reflection, we have, when it's negative in front of the function, reflection is on the x-axis. So if I have negative f of x, reflection, reflect on x-axis. And if I have negative x, reflect on y-axis. So that's the review. All right, so now what are the functions that you have to memorize? Right? Functions. Here are some basic functions and their graphs. Free of charge. This is not a part of calculus. None of this. The first one is obviously a linear function, but that linear function also includes the constant function. So I want to start there. Constant. Constant function is going to be f of x equals some number c. And that's just going to be horizontal line through c. Wherever that c is. Has to be somewhere. Linear function. You better know y equals mx plus b, right? Except we are using f of x, so f of x equals mx plus b. And that's going to be some kind of linear function there. The value which it cuts is b, the one from the formula actually. Quadratic. F of x equals to ax squared plus bx plus c, and we know that's a parabola. Cubic. F of x equals ax cubed, plus bx squared plus cx plus d, and I'll just draw a squiggle. So x cubed goes like that, and then let's say x minus 1 cubed. No. Well, let me give an example here. Also, y equals x cubed, whose graph goes like this. So to shift this function now, you will have to pick the middle point over there and move it left, right, up, down, and so on. So that's a cubic function. Let's exhaust polynomials. We have radical function. F of x equals square root of x. We already had this graph. Rational function. With f of x equals 1 over x, and this will come to play many times. And I know we still have to do e and all that. Okay, so let's go with the exponential function. And the exponential function, just in the general, is b to the x, and its graph we already had for population. Now e is special case, so I am going to talk about that. And logarithmic function. Which is the inverse of exponential function. There we go. Perfect. So we have constant function, linear, quadratic, cubic, radical, rational, exponential, logarithmic. And then we have 3 trig functions. Sin x, which ends at 2 pi, pi in the middle. Cosine x, pretty much that's the same. And tangent x. So tangent x will have asymptotes. And there will be infinitely many of these to the left and to the right. So those are the basic functions. You shift them left, right, up, down, you reflect them. Stretch and shrink, as I said, not as noticeable and visible here, but we definitely can do that. So this is the list of things that you are going to see. Now I just want to give an example from your pre-calculus. So graph y equals 3 over x minus 2. All right, so this 3 is going to be a vertical stretch. Generally, we don't care about that, right? What we care about is this minus 2, so x minus 2 in denominator. What do I know? Why is this thing charging so slowly? So, what do I know? I know that the default graph that I want to graph is this one. Right, that's the default graph. And we can see 2 asymptotes. There's a horizontal asymptote and a vertical asymptote, and the graph follows those. So with this minus 2, which is shift to the right, I get to move the vertical asymptote from 0 to 2. So to graph this, I still have my horizontal asymptote at y equals 0. My vertical asymptote moves x equals to 2. And now I draw the same function. The function looks the same as the original one, except this is moved to... And now times 3, well, the 3 is just going to introduce less of the curvature here, so it's going to be flatter because all of the values rise 3 times as fast. So to graph any of these, oh, I forgot the absolute value. Let's talk about absolute value. Which brings us to piecewise functions. I'm going to try them all. All right, so what does the absolute value do? What is the... Okay. So the consequence of having absolute value is to make numbers positive. Is that the best answer you can give? So let's talk about absolute value. So what I have is absolute value can be applied to any function. Absolute value measures the distance of a number to 0, which is the reason why it's always positive. If you're in a car with anyone and that person drives in reverse, the speed will still go positive way. There's no negative 10 miles per hour or 15 miles per hour, right? So when I say, this is going to look weird in the beginning, but then we'll clear it up. Absolute value of 3 is 3, and absolute value of negative 3 is 3. These 3's are not the same 3's. They're different 3's. Now let's see in which way. So if I have my axis over here with 0, 1, 2, 3, and negative 1, negative 2, negative 3. So these black 3's are the black 3's on the line. I'm going to change these other 3's into, that's too dramatic, let's go blue ones. So now what are the blue 3's? The blue 3's are the values that are the distances. So you have 3 hops this way, and that's that 3, and the 3 hops this way, and that's that 3. So the black 3 is a location where the blue 3 is the measure of a distance. Who would say that 3 is not the same as 3? Right? Anyone had that just explode or no? So we still good? Think about it. Look at this. 1, 2, 3. Like 1, 2, 3 in terms of people. I hope. Right? And then over there, 3 on the clock. Right? It's not the same 3. Right? This is a 3 in terms of hours, and then 3 in terms of people or desks or trees. Right? It's not the same. So 1 3 is a concept of location. The other 3 is a concept of a distance. Now distance is never negative, right? If your house is 10 miles away from RVCC, well, okay, then RVCC is 10 miles away from the house. And no matter which location you are, you have to go positive 10. That's the deal. Now, which is the reason why absolute value is always positive, because it gives us the distance. Now, if you're thinking about the function y equal absolute x, you can put f of x equals absolute x, whatever. Absolute value will take any negative number and bounce it into the positive realm. So what is the function y equals x in terms of a graph? Y equals x is a 45-degree line like this. But we are not allowed to have the negative part. It bounces up, which is the reason why the absolute value graph is this V-shaped graph. Because the negative value bounces up, the positive value of the line stays where it is, and you get your absolute value graph as is. But now you can apply this. You can apply this to any function you can possibly imagine. And you will get the same idea. For instance, what is the y equal absolute of sine x on 0 to 2 pi? Well, you know what the original sine x is. Why is that? You are not allowed to have this, so that bounces up. And that would be the absolute value graph. So anything for the graph that goes below x-axis will bounce up, and you will have your graph of the absolute value. So you don't learn, a special graph for this. This is more a procedure, right? In terms of you are not allowed to have anything below x-axis because absolute value bounces everything up. And you just reflect it in the mirror, right? It should look the same on top. Okay, exercise for you. Y equals absolute ln of x. I did not put ln function on the list of basic functions. I just remembered, so here it is. But now who remembers the ln function? Ooh. This is going to be interesting. Now you know that ln function, I did say this, is inverse of e to the x. And if you know the relationship, you can get it that way if you don't remember the function. You shouldn't be plugging in numbers, though. It's not going to go too great. So we're not allowed to have the one on the bottom, right? So it should go this way. So it has that spike at 1. Well, most of them do have spikes, right? Now, x squared, we don't have to fix it at all, right? X squared is already all positive. So, no change there. Now, if you connect that to the other concept, any number you square is always positive. Obviously, absolute value will have nothing to do there, because the entire domain, the entire range of x squared is already positive, so absolute value would have no effect on that graph. You can draw x squared in your notes if you want to. Good. Function composition. First off, let's all agree that function is computing number. Yes?
Never mind.
That's the second time. I don't just look like elephant, I remember like elephant. Don't worry about it.
I was just going to say that class ended.
So? There we go. All right, so function composition. It's like that matters. It doesn't matter. But thank you for being pro. You have nothing else to do. I mean, it's like do function composition. I mean, anyone can leave at any point in time. I'm never upset. I already said about, right? All this stuff is going to be us. So if you have to go, be somewhere. The door is right there. The window is right here. It's fine. If you can do the Houdini thing through the wall, by all means, right? There's the air duct right there too. So you have options in life. Function composition. We only have two more things. So function composition. Again, this is when you plug one function into another function. So the notation is f, and then this circle g, and people will still call it fog. It's not fog. It's f circle g of x, which has another notation like this, where you replace, right, x with g. So now I'm going to actually say what this means in words. Replace every x of f with g of x. Let's see the example. So say you have x squared plus square root of x minus 3, and g of x is sine x. What is f composed with g? Well, it's f of g of x, which means that every x of f is going to be replaced by g. So I have g of x squared plus square root of g of x minus 3. And now, because g of x is sine x, I know that this is sine squared x plus square root of sine x minus 3. And yes, you can go the other way. G composed with f is g with f plugged in. So g is sine, and its x gets replaced with the whole mess of things from above. So this is the way you compose functions. You plug one function into another function, and they become one new function. The new function has a different domain, has different rules, right? It's no longer just a basic function as before. What I need to make sure over here that you know is the test. So f composed, no, that's, sorry, that's next one. So inverse, the last thing is the inverse. And we are done. So these are the things you need to survive calculus, and then we'll do probably 3 sections tomorrow. So then your class preps should go up to, let's say, 2.4. You can do 2.5, it's fine. I mean, depends on your time. So inverse. Inverse is like one big undo button, okay? Think about this. Your function f of x is, let's say, x plus 5. So what is f of 3? Is clearly 3 plus 5, which gives you 8. And you have the ordered pair 3, 8. 3 was the input, 8 is the output. The inverse function, which is denoted as f minus 1, in this case would be x minus 5, is going to act as one big undo button. That means that if you plug 8, it better return the original value, which is 3. So that's what the inverse function does. Now, does every function have an inverse? Inverse function? No, it doesn't. You know, some things in life, when you mess them up, they can't be fixed. For instance, you're making a soup. The recipe is calling for 1 teaspoon of salt. You put a snow shovel of salt. There you go, soup ruined. You can't fix that unless you are willing to move the soup to the bathtub, right? But then you have to fire under it. It's just fire marshal and code is a lot of mess, right? So, or you break a vase, like every single time. If I knew this, right? Anyway, so certain things cannot be undone. So there's no inverse function. You can find inverse for everything, but there is no inverse function, right? You can, as I said, you can glue back the vase, but it's really not the same thing. So if you have, let's say, so the way to get the inverse, we have the following procedure. Swap x and y, solve for y, and that's it, and you win. So let's do this. It was let's say you have x plus 5. That was the idea. So you write, why am I doing purple? So f of x equals x plus 5, y equals x plus 5, x equals y plus 5. That's when the swap happened, which is the step number 1. And then solve for y. Y equals x minus 5. That's step number 2. And now for step number 3, you just write the inverse is x minus 5. Ta-da! The last thing is test for inverse functions. Test. F and G are inverses of each other if the composition between f and g, which is f plug in g inside, is equal to x, and g composed with f, g f of x also gives you x. We can test that with the thing above. We had our f to be x plus 5, and we had our g, which is the inverse function, to be x minus 5. When you do function composition, you replace every x of f with g. So that's x minus 5 plus 5, and you see that's x. Or if you try g of f of x, you get x gets replaced, so it's x plus 5 minus 5, and that's x again. So either way you try it, it's going to be that. It's going to be x at the end. So if the two functions are inverses of each other, there are more subtleties about restricted domain and other things. We'll get to that eventually. But this was the overview of calculus and some of the important things regarding functions and graphing and so on that we are going to use in this class a lot, especially function composition, so spend some time. Chapter 1 in your book is this type of a review, and your first homework, which is due tomorrow, is chapter 1 review problems. I understand there are 52 problems. Not all 52. Do as many as you have to, because you will find that 6 problems have the same directions. So you try the first one. If it's easy, then you can jump to the next cluster of problems. Make sure you can pretty much solve all of those, because they give you the basic ideas and rules to survive calculus. That's it. I might see you tomorrow, right? If they unlock the room, if you don't decide to stay home and stuff like that. See ya.